Welcome, cloud engineers and IT enthusiasts. In today's interconnected world, data is the new oil, and protecting it is paramount. Data breaches are a constant threat, and every day we hear about sensitive information being compromised. But what if I told you there's a powerful, fundamental defense mechanism that can safeguard your data, whether it's sitting quietly on a disk or actively zipping across networks? That defense is encryption. Today, we're diving deep into the world of cloud encryption, exploring how to secure your data both at rest and in transit, with hands-on examples using AWS Key Management Service, Google Cloud's customer-managed encryption keys, and SSL/TLS. Our goal isn't just to talk about encryption, it's to empower you with the practical knowledge and tools to implement it. We'll demystify complex concepts and walk through real-world scenarios, leveraging the accompanying code repository to show you exactly how it's done. By the end of this video, you'll understand why encryption is non-negotiable and how to apply a robust encryption strategy in your cloud workloads. Get ready to turn your cloud infrastructure into a digital Fort Knox. Let's get started. First, let's tackle the concept of data at rest. Imagine your most sensitive information, customer databases, confidential documents, application backups, sitting idle on a server's hard drive, stored in an S3 bucket, a GCS bucket, or even on a disconnected USB stick. This is data at rest. It's inactive, but no less vulnerable. If an attacker gains unauthorized access to your storage, or if a physical device is lost or stolen, that data could be exposed in its raw, readable form. Encryption at rest is like putting your data inside a heavily fortified vault with a sophisticated lock. Even if someone manages to steal the vault, they can't open it without the key. It's a critical layer of defense that ensures the confidentiality of your information, even if the underlying infrastructure is compromised. This is a cornerstone of compliance with regulations like GDPR, HIPAA, and PCI DSS. To manage these digital vault keys securely in the cloud, we turn to key management services. In AWS, that's the AWS Key Management Service, or KMS. AWS KMS is a fully managed service that simplifies the creation and control of cryptographic keys used to encrypt your data. Think of it as your trusted key master, an unassailable entity that guards your most precious secrets. With KMS, you create customer master keys, or CMKs, which are the primary logical keys that represent the encryption key material. AWS services like S3 for object storage, EBS for block storage, and RDS for databases seamlessly integrate with KMS, allowing you to encrypt data at rest with minimal effort. KMS handles the complex aspects of key storage, access control via IAM policies, key rotation, and detailed auditing, drastically reducing your operational burden while enhancing your security posture. You define the policies, and KMS enforces them, ensuring only authorized entities can use your keys. Now, let's make this concrete with a hands-on example using AWS. Our accompanying code leverages Terraform to provision an AWS KMS key and an S3 bucket configured for default encryption using that very key. This means any object uploaded to our designated S3 bucket will automatically be encrypted using the KMS key, without any application-level changes required for basic storage. But we'll go a step further. We'll also use a Python script to demonstrate direct, application-level encryption and decryption of a local file using the AWS KMS API. This illustrates the flexibility of KMS. You can rely on server-side encryption for integrated AWS services, or programmatically encrypt data within your applications before it even leaves your server. This empowers you to protect data at any stage, from your local file system to cloud storage, all managed by AWS KMS. Shifting our focus across cloud providers, Google Cloud Platform offers a powerful equivalent for data at rest called Customer-Managed Encryption Keys, or CMEK. Similar to AWS KMS, GCP CMEK allows you to use your own encryption keys for data stored in various Google Cloud services like Cloud Storage, BigQuery, and Compute Engine persistent disks. The key distinction with CMEK is the heightened level of control you get over your encryption keys. While Google still manages the underlying physical infrastructure and cryptographic hardware, you maintain direct control over the key's lifecycle, including setting custom rotation policies, managing access permissions, and initiating key deletion. This offers a stronger security posture for organizations with stringent compliance requirements, as it separates the responsibility of data storage from key management. You are the definitive owner and operator of the key material's logical representation. To solidify our understanding of GCP CMEK, let's dive into an example using the provided code. We'll again utilize Terraform to set up the necessary Google Cloud resources. Specifically, Terraform will provision a GCP KMS keyring, which is a logical grouping of cryptographic keys, and then create a crypto key within that keyring. This crypto key will serve as our CMEK. Following this, Terraform will configure a Google Cloud Storage (GCS) bucket to use this newly created CMEK for its default encryption. This setup ensures that any files uploaded to this particular GCS bucket will be automatically encrypted using your specific customer-managed key. A Python script then complements this by demonstrating the seamless upload and subsequent download of a file to and from this CMEK-enabled GCS bucket, showcasing how the GCS service transparently handles the encryption and decryption process using your designated key, all behind the scenes. While data at rest is crucial, securing data in transit is equally vital. Imagine your data as a message being sent through a series of tubes, the internet. If those tubes aren't secure, anyone could potentially intercept and read your message as it travels. Data in transit refers to any data actively moving from one location to another, between your web browser and a server, between different microservices in your cloud environment, or even data replicating between different cloud regions. Without proper encryption, this data is vulnerable to eavesdropping, tampering, and man-in-the-middle attacks. This is where SSL/TLS, Secure Sockets Layer, and its successor, Transport Layer Security, come into play. SSL/TLS protocols are the gold standard for creating encrypted, authenticated communication channels over a network, effectively building a secure, private tunnel through the public internet. So, how does this secure tunnel get built? It all starts with the SSL/TLS handshake. When your client, like a web browser, attempts to connect to a secure server, think HTTPS, they perform a series of steps to establish trust and create an encrypted channel. First, the client and server exchange "hello" messages to agree on encryption protocols. Then, the server presents its digital certificate, which contains its public key and is signed by a Trusted Certificate Authority, CA. The client verifies this certificate to confirm the server's identity. If everything checks out, the client and server use asymmetric encryption, public/private keys, to securely negotiate a unique, ephemeral symmetric session key. Once this symmetric key is established, all subsequent data transfer between the client and server is rapidly encrypted and decrypted using this shared secret, ensuring confidentiality, integrity, and authenticity for the entire communication session. It's a beautifully orchestrated dance of cryptography. Let's put SSL/TLS into practice with our code examples. First, we'll use a shell script leveraging OpenSSL to generate self-signed SSL/TLS certificates. It's important to understand that while self-signed certificates are perfectly fine for development and testing, they should never be used in production environments, as they are not inherently trusted by public browsers or clients. For production, you'd obtain certificates from a Trusted Certificate Authority. Once our demo certificates, a private key and a certificate, are generated, we'll run a simple Python Flask web server, configured to use these certificates, effectively transforming it into an HTTPS endpoint. Finally, we'll launch a separate Python client script that securely connects to our Flask server, exchanges a message, and receives a response, all over an encrypted TLS channel, demonstrating data in transit protection end-to-end. Beyond these practical demonstrations, adopting a robust encryption strategy requires adherence to certain best practices and considerations. Key rotation is paramount. Regularly changing your encryption keys limits the damage if a key is ever compromised. Most cloud KMS services offer automatic key rotation, which you should leverage. Always apply the principle of least privilege when configuring IAM roles and permissions for your KMS keys. Only grant access to entities that absolutely need it. Understand the difference between symmetric and asymmetric keys, and choose the right key type for your use case, sometimes even considering hardware-backed keys for enhanced security. For in-transit encryption, remember the critical distinction between self-signed certificates, good for local testing, and CA-issued certificates, essential for production trustworthiness. Lastly, regularly audit your